Hello everyone. Someone by the name Ashebar Bai requested me to do a tutorial on how to analyze data from alpha-lattice design. Alpha-lattice design is just an incomplete block design. For us to do this analysis, first we have to get data. And I'm going to extract the data from this package called methane. So I load methane to the library, and after that I am able to extract this data. I'm going to pull it out and then use it. I've pulled it out. You can see here it's here, but this name is a little bit longer for me. I want to shorten it, so I'm going to assign this data alpha just as data. I do that, and then we can view it. It's here. We have plots, replications, blocks that are nested inside replications, and genotype, and our response variable, which is yield. So next thing is just to look at maybe how many number of replications are there. These are 24. These are 3 replications. So the next thing we do is to look on how this data is. You can see we have 3 replication: rep 1, rep 2, rep 3, and then how many blocks are there: block 1, 2, 3, 4, 5, 6. Lastly, let's look at the structure of this data. You can see I'm interested with these factors. Replication is a factor, block is a factor, genotype is a factor, yield, our response variable, is numerical. Then we are good to go. Next, we load the package that we are going to use to do the analysis. We are going to do this analysis using linear models, linear mixed models, and therefore we are going to use LME4 package. We load it to the library. Another package to give us p values, LMR test to give us p values. Load into the library. I'm going to feed 2 models. The first model, I've called it fixed model, and the second is a random model. I call it fixed based on how I treat the genotypes. In the fixed model, I treat genotypes as fixed effects, and that is a blue, standing for best linear and biased prediction, or you can call it adjusted means, which you can extract using m-means package in R. So to fit this model, we'll use LMER function of LME4 package. We place the yield here, which is our response variable, and then genotype, which is a fixed effect, plus replication, which is random, and then blocks nested in replication, random, and then we specify that our data is the object that I call data, and we run. That is it. The next thing is to run the analysis of variance, and we are going to use this analysis of variance ANOVA function here on this model, the first model, the fixed model. However, it's going to return the ANOVA for fixed effects only, which is genotype. So when we run this, you see here it has only brought the ANOVA, analysis of variance for genotypes, and these are sum of square, and this is the probability, and you can see the significance. But to get the rest, we need to use other strategies. The next thing we do, let's run the summary of this fixed model, and when we run this, it's going to give us some ANOVA-like object here arrangements. We have groups, replication, that's replication here, and blocks nested in replications, and these are variances or their mean squares, but we don't have the probabilities. On this mixed linear model, where we have some other factors as fixed, we can get genotypes, the fixed effects, as these factors, the fixed effect factors, we can get their individual probability. However, this probability is compared with an intercept. An intercept is just one genotype that the model picked, which is genotype 1. You can see we don't have genotype 1 here. It was taken as an intercept, and compare to each of these genotypes to give the p-values. However, to get the probability and to judge if you have significance on these groups or these factors, you use R-ANOVA. We run the R-ANOVA, and it's going to give you the probability here of these random factors. Okay, that is it. The next model is the blab, or the random model, where we take genotypes as random. Here in this case, everything is random. It's the same like the fixed, but now the genotypes have been taken as random. We just run this. After running that, we don't have any fixed factor here. So what we just run summary. Because we don't have fixed factors, so it's not going to give us individual genotype in relation to an intercept. It's going to have these groups and their variances or mean squares. What we need to do is to get their probabilities. Again, we use R-ANOVA, we run, and it gives us the probability here. So that is it on how to analyze alpha-lattice design. The next thing maybe you may need to know is how to extract the blues and the blabs. I said if you want to extract blues, which is just a means, you use m-means package, and if you need to extract the random effects, use ranef function. Another thing that I feel that I should show you is how to compare the efficiency of lattice or incomplete block design or alpha-lattice design with randomized complete block design. This data here, we can ignore blocks and analyze it as randomized complete block design. We use RMR, we put our response variable, our factor genotype here as a fixed effect, just as the first model, the fixed model, and then the replication, but ignore the blocks, and we run. So to compare this, the easiest way to compare is to use ANOVA. You put ANOVA, you want to look for ANOVA for this RCPD model, and this is alpha-lattice model. Then we run. So in this, the result that comes out, you look at what we call AIC, which is archaic information criterion, or you can also look at Bayesian information criterion, BIC, but let's look at AIC. The model that has the lowest AIC, archaic information criterion, is the more reliable model. Therefore, incomplete block design or alpha-lattice design is more reliable compared to RCPD. That's all. I hope it's helpful, and thank you very much for taking your time. Kindly subscribe if you haven't, and also share for others to benefit from this model, from this tutorial. Thank you.